What's up guys? It's Brian here and I'm going to be solving question 12 from Unit 5 of the Physics C E&M workbook by John McGeHee or McGeHee. So our question for today is, in the drawing at the right, assume the batteries have no internal resistance. Alright, so I'm going to be I'll make the drawing later. Let's just read out the question first. A. Find the current through the three branches of the circuit. B. Find the difference in the potential between points A and B, and where that is something you'll soon be able to know. Alright, so let's move our question down real quick so it's not blocking us. Actually, you know what? I'll take it out. And let's get started on our drawing. So we have one resistor here, and then it goes out over here with another resistor, and then down you go, and there's a battery over here, and another resistor, and let's go on this side. Here's another battery. Let's make sure the lines are quite easy to tell. Alright, and then we go down and to the right, and there's another resistor over here. Alright, perfect. And then that guy connects back up here. And then we have another branch over here. Alright. And then that's a resistor and another battery over here. Alright. And this is a junction point, and we'll label this A, and this one down here, B. Alright, so that's our basic circuit. And so first thing we gotta do is we gotta label what we know so far. Alright, so let's take, actually let's first label our positives and negatives. So we have our first battery here. We'll label this E1, and we have it at 2 volts. Alright, and this is positive and this is negative, if you know how to read these things. And we'll label this guy as E2. She has a she has a voltage of 4 volts. Alright, nice and strong. And this is positive, and this is negative. Alright, on to our last battery, E3. She has a voltage of 4 again, just as strong as E2. Positive, negative. Alright, now we gotta just make a big decision. Which way is our current? Alright, so as you can tell, E1 is the weakest one right here. So it most likely will be suppressed by E3 or E2, right? So most likely our current is gonna go against E1, alright? So let's try that. Alright, so from this branch here, our current is gonna go this way. That is I1. Alright, intuitively, we can probably guess that our branch over here is going to go up. That's the direction of the current. So let's make it that way. I2. And since this guy is the strong guy compared to this guy, the current's probably going to go his way. Alright, so that's I3. This way. Okay? And now that we know our supposed direction of the current, let's label our resistors. And we should also know our values of the resistors. So our resistor here most likely is positive. This one's negative. We'll call this guy resistor 1. She has a voltage, nope, not a voltage, a resistance of 1 ohm. Alright, this guy over here, No, let's follow our current. This guy over here, this is a battery, and as they said, just in case, a battery might have internal resistance, but our question stated that there is no internal resistance, alright? So that's good for us. We don't have to label any positives and negatives, and we don't have to take care of any little r's. How convenient. Alright, so let's go into here. That, plus and minus. And we'll label this 1, 2, 3, 4. Okay, alright, this guy is R4. And she is going at 1 ohm too. Alright. And let's move on to I2. Again, no internal resistance in the battery. No need to worry. Positive, negative. We'll call this guy R3. She has a resistance of 2 ohms. Let me put that over here. And over here, oh, is that R3? Yes, that's R3. And then we're done with branch I2. Let's move on to branch I3. Okay, so we're starting here. Positive, negative. This guy is R5. She has a resistance of 1 ohm. This one over here, R2, positive, minus, be clear, resistance of 1 ohm too. Alright, so that's a little handy dandy for us. The ones on the outside are 1 ohm and one on the inside is 2 ohms. So that's all nice and swell. Let's go on and make this diagram a little smaller so we can have space to write our equations. Alright. Perfect. Let's make it a little smaller. That should be easily readable. Alright. And let's move it a little out here. Alright. Okay, so let's get started with our equations. And actually, no, first let's define our loops. Alright, so we will probably want to follow which way is the current going, right? So in general, we can sense that it's going counterclockwise. So let's do that. Our loop 1, nope, I meant brush tool. Loop 1 is going counterclockwise. And we'll say the same with loop 2. Alright, so let's get started with our loop 1 equation. So let's start over here with where branch I1 starts. So we're first met with a resistor, R1. So, as we all know, first, V equals IR. Ohm's law, never forget. And in fact, it's probably unforgettable. He's unforgettable. You know what? Most beautiful law, unforgettable. Second, right behind F equals MA. Alright? So V equals IR, don't forget that. And then another thing we need to know about Kirchhoff's law is the voltage going in equals the voltage going out. Actually, no, not in. The voltage increasing equals the voltage decreasing. Alright, so we'll just follow that. If it's increasing, going from negative to positive, like over here, negative to positive like that, we'll put it on the left side. And then if it's going on from positive to negative, we'll just put it on the right side, over here. Alright, with that in mind, let's first set our equal sign. Let's not make it too big. So we first have resistor 1, I1, R1, following Ohm's law. Alright, that's our voltage. We want to set it in voltage, so that's why we follow Ohm's law. And now we have E1. Now notice, we're going against E1. So that means instead of positive change in voltage, it's decreasing now. So we want to keep it on the right side too. And also notice we don't need Ohm's law because this guy is in volts already. So E1 right here. And now we have resistor number 4. Ohm's law again. I1, R4. Let's move this guy over a little. And let's continue writing. And now we're on branch 2, so everything needs to be an I2 now. So we have another battery here, and notice it's going from minus to positive, so negative to positive, so that's an increase now. So that's, oh, wrong side. Wow, even I messed up. Alright, E2 over here, and since it's in volts already, we do not need Ohm's law again. Be careful. So, and so now we come to our final resistor, R3, and that's I2, R3 following Ohm's law. Alright, so that's our first equation for loop 1. We included branch 1 and branch 2. That's awesome. Alright, so now let's make this a little smaller so I don't have to take up too much space. Alright, and with that in mind, let's start loop number 2. Let's start where I3 starts, right over here. And with Ohm's law and Kirchhoff's second law in mind, let's set up our equation. So we're met by resistor 5 first. Notice it's I3 this time, so I3 and R5. Okay, Ohm's law just like usual. Alright, and now we have a battery. E3. Notice it's from negative to positive, it's in volts, so it's on our left side, and we don't need Ohm's law again. Alright? Let's write that again. There we go. And now, resistor 2. I don't think I need to say it anymore, right? So, I3, R2. And then we have resistor 3 again. Notice it's backwards, so we can conveniently just put it on the other side now. And same with E2. So why don't we put this guy over here? Alright, and I believe that's our equation here. So let's make this guy a little smaller too. Alright, and then we'll put this guy right next to our first equation for loop 1. And now let's do a count to see we have every object included, because that would be a disaster if we don't. Alright, so we have E2, 1, 2, 3, 4, 5. Alright, 1, 2, 3, 4, 5. Alright, that's perfect. Alright, so loop 1 has every object in there. Let's check loop 2. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Alright, so everything's included. Now, we need one more equation, and you'll see it comes in mighty handy. And that's following Kirchhoff's first law, and that's any current going in, the summation of the currents going in has to equal the summation of the currents going out. So basically anything going in has to be the same as anything going out, at least in value, following conservation of energy, of course. So with that in mind, let's make our our final equation. So I3, okay, let's take junction A. I3 is going into junction A, and same with I2. So let's put that on our left side since it's going in. And I1 is the only one going out of junction A. Alright, nice and solo. Oh, not 2, but 1. Alright. You're the only one. So let's put that make that smaller. Alright, so I don't think we need these guys anymore. Thank you, Kirchhoff. Thank you, Ohm. And now let's put these guys over there. Oh, careful. There we go. So with these guys, let's substitute the numbers we know into our loop 1, loop 2 equations. Alright. So with our loop 1, we have E1, 2 volts. Oh, nope, E2, sorry. That's 4 equals I1, R1. So I1, R1 is right here. R1 is 1 ohm in resistance. So since it's 1, no coefficient. How convenient. Now we have E1 over here, 2 volts. Let's make that look a lot nicer. Nice. Now we have I1, R4. Where is I1, R4? Over here. Alright. He also has 1 ohm, so don't need the coefficient. I2, R3. Over here. Careful, 2 ohms. Alright. So we'll just put our coefficient in front. Remember, this is the resistance over here. Our coefficient is the resistance. So 2I2. That's our first equation. Alright. Actually, you know what? Why don't we just solve this along the way? Or at least simplify it. So this guy becomes... Actually, let's move it down. This guy becomes... So this guy cancels to become 2. So 2 equals 2I1 plus 2I2. And guess what? We can simplify it a little more. 1 equals I1 plus I2. How elegant. Alright, so let's take away those little more complex equations. Alright. Okay, so let's replace the loop 2 numbers. Okay, so what's E3? E3 is right over here, 4 volts again. So 4 plus I2R3. So we remember I2R3 over here was 2 ohms and I2, so 2I2. And that equals I3R5. R5 is right over here at 1 ohm. No need for a coefficient. How convenient. I3R2, same thing, 1 ohm again. So just add I3 again. E2, right over here, 4 volts. Huh, how convenient. Our constants cancel out. Bam. And we're left with 2I2 equals 2I3, which becomes I2 equals I3. Okay, that's really simple. And now we also know that our I2 and I3 should be the same in magnitude. If they're not, we got some problem. So let's move this guy over here too. Okay, and now we got another handy dandy equation we didn't think about. I2 plus I3 equals I1. So let's first substitute this guy into this guy. Alright? So we'll take a different color. Don't select 1. No, we didn't want that color. We wanted brown. 1 equals I2 plus I3. Since I1 equals I2 plus I3. Alright. And don't forget our final I2, that's lying around over here. So don't forget I2 equals I3. So let's take it one step further. That's I2 plus I2. Hey, guess what? One variable. So now we can solve it. 1 equals 3I2. So now we know I2 equals 1/3 of an amp. Nice. And with that in mind, since I2 is 1/3 of an amp, wouldn't that mean I3 is 1/3 of an amp? You betcha. Alright, so we have two of them solved. And guess what? With I2 and I3 known, we can just plug it back right in here. That equation gives back like there's no tomorrow, isn't it? Alright, so let's do that right now. With I2 and I3 both 1/3, we can fairly conclude that I1 is 2/3 of an amp. Okay, let's rewrite that one more time. Nice. Alright, so we don't need any of this work over here because we're done with it. Thank you very much. And this guy is also done. Thank you very much. Okay, now. Okay, now let's check our signs first. Remember, these guys are all positive. Positive, positive, positive. So that means that we guessed our currents right. Nothing is going backwards for us, which is good. So that's problem A. Let's get on to problem B. And let's take out the question again. So part B is finding the difference in potential between points A and B. Alright. Well, now we know our current, we can just use Ohm's law again to find our resistor, the voltage on a resistor, and conveniently we have the voltage for that. Alright. Okay, so let's take a different color again. Let's take a nice old blue again. So our current goes this way, right? So when we start over here, there's no potential difference between the 2 points. At least if A is over here instead of over here. So we start with 0. But notice. Alright, let's write B to A. That's the way we want to go. So if you notice over here, it's a 4 volts in increase, so we can just simply put 4 volts in here. That's plus. But every time we meet a resistor, it's a decrease. So let's subtract that. And using Ohm's law again, V equals IR. That's I. Let's just substitute that in. So I2, 1/3 of an amp, times R3, which is, as you know, 2 ohms. And now you're wondering, amps and ohms don't add up, don't they? Now remember, ohms actually equal to volts over amps. So if you think about that, why don't we replace volts, ohms with volts over amps? So these guys cancel out, and you end up with volts again. So really, that's actually just 4 minus 2/3 volts. Okay? Which means that VA really is equal to, I believe, 10/3 of a volt. Okay. So that's our difference between B and A. So let's make a little small review over here. Alright, let's organize everything. So that's A, and this is B. Okay, so let's review. So our question was to find the current through the 3 branches. Alright, and the way we did that was we used Kirchhoff's law, it's Kirchhoff's second law, and Ohm's law, the most unforgettable law in E&M, of course, to figure out which way. So we first guessed our currents, which way it was. Then we set up these loops and we figured out the change in voltage as we pass through each one, right? Each of these objects. And we set up these equations, all right? And then we also used Kirchhoff's first law to set up this equation at the junction. And as you can tell before, that it gave us some crucial steps to solve the system of equations. If we didn't have this, it would be impossible to solve. So by replacing these values first with the ones we know, and then solving the equation, we're able to get these simple values. And we also had to pay attention to the signs, and we were lucky this time because they were all positive, and so that means the currents we guessed were right. So that means so if they were negative, we just had to flip it around. And good point, I forgot the units, or the direction. So this one went counterclockwise, this guy went up, and this guy also went counterclockwise. Alright, so now we have your solutions here, and to find the potential difference, you just start at where the current starts, right? Or at the point at where the current starts from, and then you just move up the current and you add the batteries if you're going from minus to positive, and then you subtract if it's resistance. Alright, so I hope that was a big help to you guys, and